So let us do the next theorem, that is the density theorem, that if x and y are any two real numbers, x and y are any real numbers with x less than y, then there exists at least one rational number such that x is less than r is less than y, or in fact there exist infinite rational numbers between any two real numbers. So, for the proof of this I need to recall the previous argument which in the earlier lecture I have discussed its proof. This one. Using well ordering property, I have already discussed this in the earlier class, this corollary, that if y is greater than 0, then there exists n y at least one natural number, so which will include this y, n y minus 1 is less than equal to y is less than equal to n y, using the well ordering property, this condition. We have completed its proof. So, now do its proof here, density theorem. So, here the trick is that I need to given any two real numbers, say x and y, I need to show that this condition n x less than m less than n y. Why? Because n is a natural number. So, after dividing a natural number, so obviously n is not equal to 0. So, after dividing by n, we have r of the form p by q or say m by n. So, it is no loss of generality or without loss of generality. When the proof is similar, in that case we can write without loss of generality. See here, y, x is less than y. So, I can write that y minus x is greater than 0, and just recall the Archimedean property of real numbers, that for every epsilon greater than 0, there exists a natural number such that n times epsilon is greater than 1, or 1 by n is less than epsilon. So, whenever there is any real number, say epsilon greater than 0, I can always apply Archimedean property of real numbers. Now, even if x is greater than 0, then again y minus x is greater than 0. So, consider this as epsilon. So, we have 1 by n less than epsilon, or 1 by n less than y minus x. So, this is the first relation, or from here I can write it as 1 less than n y minus n x, or n x plus 1, let us bring it to left hand side, n x plus 1 less than n y. So, this is the first relation which is given here, n x plus 1 is less than n y. Now, use the previous corollary 2.4.6, that whenever y is greater than 0 is given to us, there exists n y using the well ordering principle such that n y minus 1 is less than equal to y is less than equal to n. So, use it for n x. X is any real number, x is strictly greater than 0 here. We have assumed this condition, and n is any real number. So, n is a natural number, x is greater than 0. So, n x is going to be a real number, let us consider it as y. So, I can use this one because x is greater than 0 and n is a natural number. So, obviously, n x will be always greater than 0. So, I can apply this one. Now, use it for n x. So, there exists, because already we have used this notation n here. So, let us in place of n, let us take n y as m minus 1 less than equal to y less than equal to m. So, using this corollary 2.4.6, we have this result that m minus 1 is less than equal to n x is less than m. Now, if we combine these two inequalities, n x plus 1 less than n y and m minus 1 less than equal to n x less than m, we have this relation n x less than m less than n y. N x plus 1 less than n y. So, combining this, we have n x less than m less than n y. Use this n x less than m. So, we have n x less than m less than n y, and since n is a natural number, so I can do division by n. We have x less than r less than y. So, using the repeated argument between x and r y, we can show that there exist infinite rational numbers between any two real numbers. So this is the idea of the proof which we have done using Archimedean property of real numbers and this corollary. Okay. Now there is another part similarly. There is a very interesting case here, which when I will come to see the concept of using countability, that see Q union set of rational union set of irrational is equal to R, and in the chapter of countability we will study that both being infinite set, this one is countable, set of rational number is countable, whereas set of irrational number is uncountable. And even the cardinality, that is the transfinite number allotted to set of irrational number is greater than set of rationals, and R is uncountable. Despite this, both sets are dense in R. That's what written here. Both sets are dense in R. That is, in other words, I can say that in metric spaces we will extend this condition, and in topology by using the concept of open set, we will use this notation. Here just I am giving you a basic idea that we used to say that the closure of Q is R, that is Q is dense in R. In other words, I can write this: if Q is dense in R, then for every x belonging to set of real number, there exists Q belonging to Q set of rational, and for every tolerance such that x minus Q is less than epsilon. So whatever the bound we will choose, or the error, or the tolerance, I can get a rational number as close as to this real number. So this is another idea, but I am not going to do it here. Similarly, set of irrational number is also dense in R. So that idea we will do in metric spaces after covering the concept of open sets. And we will see that this R under usual metric will become a special case of the metric space. Now with same idea I can do for the set of irrational, to show that between every two real numbers there exists at least one irrational, or in general between any two real numbers there exists infinite irrational, using the same repeated argument. What we will do here, see we can x and y with x less than y, again it is given here, so this implies y minus x is greater than 0. So I can use this argument that because this is already given here that x is less than y, so obviously y minus x is greater than 0. And if you recall the Archimedean property of real numbers, Archimedean property of R, then for every x y belonging to R with x greater than 0, there exists n belonging to n such that n times x will exceed y. So since this Archimedean property is true for each y, whether y is positive, negative, 0, rational, irrational, so in place of y I can take root 2, and yes, in place of y I can take root 2 because it is true for each y. So I can rewrite this statement, I can take this one as epsilon, and I can write that for every epsilon, that is y minus x strictly greater than 0, this is the statement. This x and y are, I have referred for Archimedean property of real number. Here for this case, since their difference is strictly greater than 0, so I can always apply this trick here, epsilon greater than 0, such that for every epsilon, that is y minus x greater than 0, there exists a natural number, at least one natural number, such that n times y minus x is strictly greater than root 2, because I need to bring it into irrational form. I need to show that between every two real numbers x and y there exists at least one irrational number. So this is the idea here, and using this I can from this here I have y minus x is strictly greater than root 2 upon n, or I can also express it as y greater than x plus root 2 by n, x plus root 2 by n, and x plus root 2 by n, because root 2 is positive, n is positive. So, I can write that y greater than x plus root 2 by n, this one is greater than x. So, we have the first equality here. Similarly, if we can see that x plus root 2 by n, this is greater than x plus root 2 by 2n. Why? Because we are dividing here denominator here by 2. So, this number will be less than x plus root 2 by n, and obviously greater than x, because in x we are adding a positive number, and y is greater than x plus root 2 by n, x plus root 2 by 2n. So, from this inequality, from this condition, if we take the difference of these two, say x plus root 2 by n minus x plus root 2 by 2n, this difference, then we will get root 2 upon 2n. Now, since the difference of these two numbers is an irrational number, root irrational number, this implies that at least one of these two has to be irrational, So, in between x and y, we have constructed at least one irrational number. Again, we will use this argument, if this one is irrational, again, or say rational, again use the repeated argument, and we can show the next irrational number. Using the same argument, one construct the next one. So, this is the idea for density theorem, So, we can see that everywhere we are using either Archimedean property of real numbers. These, how important is Archimedean property of real numbers, and the well ordering property. This is the characterization of interval. Just we need to recall the definition of interval. S is a subset of R that contains at least 2 points and has the property that if x y belonging to set S with x less than y, then the whole ray has to be contained into this set. Then we will only say that S is an interval. For example, 0 1 union 5 7 is union of interval, but not an interval. Why? Because whenever if we are calling this as set S, and if it is an interval, so for as per definition for every x y, so let me take x equal to say 0.5 and y is equal to say 5.5 with x less than y, with x less than y, then every real number, lying in between x less than z less than y. If I choose z is equal to say 2, 0.5 less than 2 less than 5.5, then one can see that 2 is not member of the set S. That is, the whole ray has to be contained into the set S if it is interval. So, this is union of interval, remember, but not an interval. These are the say A is equal to 5, empty set is called the trivial interval. A is equal to 5, and this is called the singleton set. Say B is equal to say singleton, just for symbolic representation, let me take this one. So, I can write it as closed interval 1 to 1, and this I can write as open interval, say 1 to 1. We are not including 1, so I can call it as empty set. So, this one is the phi and 1 singleton, phi empty set and singleton set both are trivially interval. But this one is an important remark, that union of interval need not be always an interval. So these are the example of examples of intervals. So for example, open interval 2, 3, any closed interval without the gap, say 4, 7, or open at 4, closed at 7. All these are intervals, including the trivial intervals. These two are called as trivial intervals. So overall, remember that whenever we are calling any subset of real number as interval, this means for each z lying within x, y, where x and y are coming from that set, z has also to be within the set. If there exists at least one element which is not member of the set, then we will say that this subset is not an interval. We will use it in some proofs. So I am closing it here, and the next theorem we will, in next class we will, in next lecture we will do this one, decimal representation of real numbers as well as nested interval properties.